Hola, physics friends, and welcome to a video where I'm basically going to go through all the problems on the 6.2 practice problems. It's 12, 13, 14, 15, and so on. Feel free, you're going to be able to fast forward to wherever you need to get to see what you need to see to help you understand what you need to understand. Let's get started. So I put all these questions over here in a Smart Notebook file so I could do them over here. Let's go. Number 12 says, a runner is moving at a speed of 8.8 meters per second, rounds a bend with a radius of 25 meters. So here's my track. Here's my person running. There's a few forces on them. Number one, there's a force straight down, force of gravity. Number two, there's a force supporting them, the normal force, and then there's a force that's making them turn the corner, and that's the centripetal force. What's the centripetal acceleration of this? The centripetal acceleration is always your velocity squared divided by your radius. Maybe they're just so nice that they give us everything. Oh, 8.8 divided by my radius of that, they tell you that, 25. So 8.8 squared divided by 21, and you get 3.1. And since it's acceleration, it's meters per second squared. So when you're going around the corner, you're always accelerating towards the center at 3.1 meters per second squared. That's number 12. Number 13. Same idea. You've got a racing car going around a curve. So there's my curve. Here's my racing car. Kind of hard to kind of show that. There's a force straight down of gravity. There's a force straight up. That's a normal. And if you're turning a corner, the centripetal force is turning you. Find the car's centripetal acceleration. So that's the first part. Centripetal acceleration. Velocity squared divided by radius. So my velocity is 22 squared. My radius is 56. So when I do all that, I get 8.6. And what's the minimum coefficient of static friction? Whenever you turn a corner, whenever you turn the corner, friction is what turns you. Maybe you've run around a corner and you run around ice, and you realize that friction is really important to turning because your body will go straight. You'll slip and you'll fall and you'll go straight. Happens in, I've been watching a lot of F1 racing recently, and you can totally tell that. So the centripetal force, friction is what turns you. So I'm going to use this idea right now. I'm going to set the force of friction equal to the centripetal force. And the friction force, remember, is always the coefficient times the normal force. And the centripetal force is your mass times your velocity squared over your radius, which is a short way of saying it's your mass times your centripetal acceleration, which we already found. Your normal force, you'll remember, is since it's opposite gravity, whatever the mass is, it's multiplied by 9.8. That's what the normal force is. It's whatever your mass is times 9.8. So my normal force is 9.8 times my mass, m. And you'll notice that there's a mass on either side of this equation. So it doesn't matter what you put your mass is. So maybe you're saying, Mr. Hare didn't tell me my mass. It doesn't matter. If they don't give you something that you probably need, then most likely you can make it up. And any number you would have made up would have worked out. So my coefficient of friction times 9.8 is equal to 8.6. So if I take 8.6 and I divide by 9.8, I find my coefficient of friction. And that turns out to be 0.88. So you need pretty sticky tires to go around at that speed. Next question. Number 14. An airplane is traveling and makes a turn. What's the smallest radius that the pilot can make and keep the centripetal acceleration under 5 meters per second squared? All right, so here we go. We'll make a picture here. Got this airplane turning in a circle, and they want to know this radius r. If you go too fast in an airplane, you can pass out because you'll fling the blood to the bottom of away from your head and you pass out. So there's a maximum that you can do. In reality, it's like pilots with training. I think 4 Gs is kind of running around the maximum. You and I don't know if we get anywhere near that. So centripetal acceleration is velocity squared over the radius. We want the centripetal acceleration to be under 5. My velocity is 201. And we just got to make sure that this is meters in seconds. This is meters in seconds. We're good. We're good to throw those numbers in there as they are. So we solve this for the letter R, and it turns out to be 8,100 meters. Also known as 8.1 kilometers. Either one, totally acceptable. Number 15. A merry-go-round worker stands on the ride's platform, 6.3 from the center. If her speed as she goes around the circle is this, what's the force of friction necessary to keep her from falling off? So you've got this merry-go-round, and there's a person looks like she's sitting. And if you spin too fast, then you're going to get flung off. So the question is, what's the force of friction? So remember, the force is on you. There's gravity, there's a normal force, and there's a force that's turning you in a circle, the centripetal force. And friction is providing that. She could be holding on to a handle, and that would also supplement her turning centripetal force. That could help her go faster around the corner. Maybe you've run around a corner and you grab a pole and you can really rip yourself around a corner. Same idea. So friction is going to do this, and here's where I'm going to start. Friction is equal to the centripetal force. She's 45 kilograms, so you know if you take 45 times 9.8, you get 441 newtons. That's the normal force. The force of friction is the coefficient of friction times the normal force. What do they want? What is the force of friction? So they actually want to know this whole quantity. So you know what? I'm not even going to break that down. I'm just going to leave it as the force of friction. The centripetal force is your mass times your centripetal acceleration, which is your mass times velocity squared over radius. My mass is 45. My velocity is 4.1. And my radius is 6.3. Oh, that's kind of nice. So I multiply all these things together and I get 120 newtons. So the force of friction needed to provide her is 120 newtons. That's the minimum that you need. Well, that's what you need to turn this mass of a person at that speed in that tight of a corner. Number 63, a coin is on a vinyl stereo record. So, I don't know. You guys probably know what records are. They're kind of coming into popularity again. So there's a coin on a record. It's making 33 1/3 revolutions per minute. In what direction is the acceleration? So this coin, there's a force of gravity on it. There's a normal force. And then there's a force towards the center we call the centripetal force. These two forces cancel each other. So this is accelerating towards the net force, which is towards the center. So part A, what direction is it accelerating? Toward the center. Objects are always accelerating towards the center when you go in a circle. Part B, find the magnitude of that acceleration when the coin is placed 5, 10, and 15 centimeters from the center of the record. Okay. So the acceleration is your velocity squared divided by your radius. So my first radius is going to be 5 centimeters. I'm going to change that into meters, 0.05 meters. Now my velocity. So when you're on a record, your velocity is the distance So it goes around this record, and your velocity is equal to your distance divided by your time. And so here kind of is right now. You're going 33.3 revolutions per minute. So all I got to do is change revolutions into meters, which I can. 1 revolution is equal to 2 pi r. The circumference, right? The radius they're telling me at the onset was 5.05. And then we'll change minutes into seconds. So 1 minute is equal to 60 seconds. So minutes are gone, revolutions are gone, and now I end up with meters per second. So that's my velocity. So I multiply 33.3 times 2 pi times 0.05 divided by 60. And you get 0.17 meters per second. So I'm going to stick that in there, 0.17 meters per second. So then I can find my my centripetal acceleration. When I do all of that, I get 0.58 meters per second squared. Now I got to do all of that for 10. So I'm going to change my color, and I'll do blue. So 10. So I'm going to just change everything. I'm going to put 0.10 in here. And then I got to change this problem over here, this part of it, 0.10, because it's still going to 33 1/3 revolutions per minute. The only thing that changes that. So then this ends up doubling, and I get 0.34. So I put that in there, 0.34, and I end up with, for an acceleration, 1.2 meters per second squared. And now I'll use green in my final one. These 15 centimeters. So again, kind of get rid of these ones and put 15 here. And then instead of that, I'm going to put 0.15 there. And I don't get 0.34, I'm going to get 0.352. So I put that there. And then I end up with 1.8 meters per second squared. That's part B. Woo! This is a brutal question. Part C. What force accelerates the corn? What is actually causing this force right here? Friction. Friction. And then part D. At which 3 radii would the coin most likely fly off? It's totally going to fly off at the farthest because it has the, number one, it's going the fastest. It's going the fastest at that point, and which makes it have the most centripetal acceleration. And since the mass is the same in all of these, the centripetal force is your mass times your centripetal acceleration. So if this is the biggest, and then you multiply by the mass, you're going to have the largest centripetal force when you're going with the largest centripetal acceleration. Woo! So part D. At 15 centimeters. What a brutal problem. 74. Early skeptics of the idea that the Earth would rotate said that the fast Earth would throw people off if because we're spinning. The whole Earth spins all the way around once a day. That's gonna fling people off. You know, what if Earth automatically stopped? Like people would go flying forward. It would be just the wind would happen. It would be just a nightmare scenario if the Earth suddenly stopped spinning. Show why this idea is wrong. The radius of the Earth is this. What's the speed of a 97 kilogram person at the equator? Okay. So part A. The thing you're going to have to know about Earth is you're going to have to look up the radius. And they give you the radius. That's kind of nice. They tell you the radius of Earth is 6.38 times 10 to the third kilometers, or 6,380 km, or 6 million meters. A really great story is how did they figure that out? There was a guy a long time ago in ancient Greece. His name was Eratosthenes. He was a librarian at the Great Library of Alexandria. And on the what's called the solstice, where the sun is highest in the sky, solstice it's exactly above the equator. One of his friends wrote a letter saying, "Hey, on the solstice, I can see my shadow all the way to the bottom of the well." And he's like, "Well, up here in Alexandria, we can't see the shadow." So he did a little bit of geometry just from the shadows down a well, and he figured out exactly how far the circumference of the Earth was, to within 3%, which was like an incredible amount at that point in time. So, fun side story. What's the speed? Okay, so your velocity is going to be equal to your distance divided by your time. So somebody on the equator, they're going to go all the way around the Earth once in a day. So your distance is going to be the circumference, and the time is going to be 24 hours. So the circumference is going to be 2 pi times the radius, 6,380, and I'm going to add 3 more zeros because that's meters, divided by, 24 hours. So when I do all of that, I'm going to end up with, except I'm not going to do 24 hours. I'm going to make it into seconds. So like 24 hours, and there's 60 minutes in an hour, and there's 60 seconds in a minute. So I do all of this, and I end up with 463 meters per second. So that's how fast you're going. Woohoo! You're cooking. You're almost going the length of a track every second when you stand on the equator. You're going more than the length of a track. The part B, what's the force needed to accelerate the person in the circle? So, part B, the centripetal force is mass times velocity squared over the radius. So my mass, a person, 97 kilograms. The velocity, 463 squared. The radius, again, 6,380,000. So that force is 3.3 newtons. Kids in the Kings, that's only 0.7 pounds. It only takes not even 1 pound to get a human being spinning around Earth on that orbit. It's not a lot of force. Part C, what's the weight of the person? The weight of the person is going to be 97 times 9.8, which is going to be like 950 newtons. Holy cow. Earth is attracting you with a huge amount of force. It only takes 3.3 to do this. What's the normal force of Earth? Ooh, this is a great question. Let's talk about that. So here is planet Earth. And Earth is attracting you with a force of 950 newtons. So then there's 3.3 newtons it takes to actually accelerate you in that circle. So you need to have a net force in this direction of 3.3. Because if you have a net force in that direction, then you have the acceleration that you need to go in that circle. So the normal force is going to be 3.3 less than this. So 900 and boop, boop, boop. What is that? 46.3. 947. It's very, very small. Very, very small difference. It's like 1/3 of 1% difference, and that is what accounts for us staying on planet Earth. Not a big deal. That's a crazy question. Number 61, a car going around a circular track. So I'm going to do an overhead view here. Here's my car. What's the acceleration and what force? So this car, remember, there's straight down force of gravity. There's a straight up force of normal, and then there's a force towards the center, which is the centripetal force. The centripetal acceleration is equal to your velocity squared over your radius. So, my velocity, boy, that's going to be tricky. It's going to be my distance over my time, which in this case, since it's circular, 2 pi times the radius, 2 pi times 50. Over the time, it takes 14.3 seconds. So when you do this, that turns out to be That turns out to be 9.6. No. Sorry. Turns out to 22 meters per second. So I stick this in for my velocity. 22.0 squared. And my radius is 14.3. So my centripetal acceleration is 9.65. That's part A. Part B. What force must the track exert on the tires to produce this acceleration? The centripetal force is providing this corner. So it's your mass times your centripetal acceleration, and we just found that. So my mass, 615 times 9.65, is quite a lot, 5940 newtons of force to do that. Number 62. So, find the centripetal acceleration. The centripetal acceleration is your velocity squared divided by your radius. And your velocity is distance divided by time. And when this thing's going in a circle, the distance is the circumference. 2 pi times the radius, which is, in this case, 1.8. And the time it takes to go around, it goes 1 revolution in 1.0 seconds. So, the velocity here is, boy, I don't know. Let me do that real quick. Is 11.3. Stick that into my velocity. So my centripetal acceleration, 11.3 squared divided by my radius, which was 1.8. And that turns out to be 71. Second part says, what's the tension? This thing is being turned in a circle. So what's providing that is the tension of the rope. So the tension, the wire is actually spinning this. So the tension in the rope is the centripetal force. And the centripetal force is your mass times your centripetal acceleration. We just found that part. So our mass, 7 times 71, turns out to be 500. But you got to write that with 2 significant figures. 500 newtons. And our last problem. Curved roads are often banked to help prevent cars from slipping off the road. If the posted speed limit for a particular curve, what angle should the road be banked at so that the cars will stay on a circular path, even if there was no friction? Oh boy. what angle? So here's a back end view of my car. So here's my wheels, here's my bumper, here's the car. Here's what's happening. Gravity is pulling this car down. And it doesn't tell you what the thing weighs. It doesn't matter. It's all going to come out in the end. So I'm just going to make up a mass of 100. So if you take 100 times 9.8, you get 980 newtons. There's a normal force going on here. And these are the only two forces, kids, that are at work right now. And here's how this car can make a corner. Remember that there's a force turning you. What turns you, believe it or not, is the normal force. When you take your normal force and it's going to be weird. We're going to break it into its x and its y component. The part that turns this is this guy right here. This is providing the force to turn us. So, the question wants to know, what angle do we need? Because this angle right here is definitely going to affect how big that is. And we need that to be a certain size to do everything. So let's work our way backwards through all of this to figure out our angle. So, the centripetal force, the force that is needed to turn me, is my mass times my velocity squared over my radius. I made up a mass of 100. My velocity, they're telling you, is 15.7. And the radius is 36. So if you take 100 times 15.7 squared, you get 684. 684. That is what this has to be. Now we go down the path. If that is 684, there is, oh boy, this has to be equal to 980 right here to make this all work. Because the down, get rid of that. The down equals the up. So now there exists some angle right here to make this work. So let's see here, inverse tangent. (34.9 degrees). There you go. So even if friction stopped, like this is why civil engineers bank corners on the highway, because if there's less friction, you can still make the corner and not go skidding off a ravine or into a tree or into the ditch, just from the sole fact that this component right here, this component turns you. Now we just do it all again if the speed limit was different. So we change this to 20.1, which then changes that number to 1120. And that number right there is this number. And then my next angle, 1120 divided by 980. So you're going to have to bank it at a bigger angle. I should expect a larger angle when I do all of this, and you get 48.8. Pow. Woo! Good work, kids.